Buenas tardes. I hope I will not be too long. It's getting late and you must all be very hungry. I am very grateful to be here. It is an honor, and I echo the comments of other speakers. We've been well cared for, and this has been an amazing experience. So I never expected 40 years ago to be at this kind of platform speaking to an esteemed group in Peru about spectroscopy, alteration, and this tool that we use to help define our ore deposits and to find new ore deposits. But I started very much as a field geologist. As you can see, times have changed. There's a little lack of PPE in this picture. I was in Indonesia, underground, obviously not well protected. But times have changed and tools have changed, and I think that what I will hope to show you is a little bit of that transition, what we were doing in the 90s, what we're doing now, and what still needs to be worked out in spectroscopy and in the tools we use in order for us to get even better information. So this is the conclusion. If you can go to lunch now if you want. But we are fully portable. We can do this spectroscopy at multiple scales. We can access our data in real time. We have huge data sets. And this has implications for exploration, for geometallurgy, for recovery, for remediation. And that's why this tool is such a valuable one. We've had very excellent introductions and discussions from Jeff Hedenquist yesterday and David Cook this morning that, of course, talked about our classic deposit models, the use of alteration, and pushing the envelope on what we can do with looking at mineral chemistry in extensive alteration envelopes, at understanding the whole lithocap environment, and SWIR and spectroscopy and other aspects of spectroscopy is just such a wonderful tool to continue to develop these models. And of course, it's not just in the porphyry environment that we use these tools. The volcanogenic massive sulfides and many other deposit types is equally useful. So we're doing this at all scales, right? And we originally started out doing this for Landsat images to understand what those images were telling us, to be able to ground truth them. So we created field portable spectrometers to go out and ground truth an image from remote sensing. That was the main driver back in the early 90s when the PIMA came out and Terry Cox gave that to the world, as it were. That was the driving motivation. But we obviously use it at all scales now. We use it to do mineralogy. We use it to analyze core. So this is the general history of using spectroscopy. And people will say to me often, oh, this is new technique. I feel David Cook's, the industry can be very skeptical for very long periods of time. But this spectroscopy has been used since the early 1900s. It was a laboratory technique. They had spectrometers in labs. They had mineral databases in the 1940s. So this is not new. What's new is that we've been able to miniaturize it, take it in the field, and now what's happened is that we obviously had the digital revolution. We have the computers. We have the ability to process data in the field and large quantities of data. And that's really what changed everything. So if we look at how we had PIMA came in the 1991 or thereabouts to be used in exploration, then CSIRO also developed the HiLogger core scanning tool as the first core scanner. And then we had introduction of ways of analyzing data with the Spectral Geologist and then OSIRIS. We've had a whole explosion of things happen in recent time. Some of the key individuals that I really look up to in this whole technique, Phoebe Hauff on the left, who I worked with for years, was instrumental. And some of you in South America, particularly, she worked here a lot, will know her work from the 90s and in the 2000s. She was detailed, she looked at compositional changes, she recognized empirical changes, and really made the tool valuable for exploration. Jonathan Huntington in the center there, again, I mentioned instrumental in the Spectral Geologist software at CSIRO and the High Logger, and really driving the idea that we could not only measure core spectrally in the short wave, but also into the long wave as well, and we'll talk more about that as my talk goes on. And on the far right, Sasha Panchal, who has retired, sadly, but instrumental in advancing our ability to process this data quickly and get really good mineral ID through the OSIRIS software machine learning technique, and we'll also talk about that more. So back in the 90s, I was here in Peru. I went up to the PAMEL project, and we mapped outcrops. So for then, at that point, that was state-of-the-art. And the fact that you could get an alteration map over a 5-kilometer square area in a day was groundbreaking, revolutionary. This is just an outcrop map. But one of the key things about it is that we were moving from grouping things into argillic or advanced argillic or based on our best guess in the field to actually being able to identify the minerals and to be able to give a mineral assemblage as opposed to lumping things into some sort of genetic connotation. So we started to map mineral assemblages, and this gives us much greater information about the areas that we're exploring. We also found that we could use one of the features in the spectroscopy. You get a feature at around the 2200 wavelength, and we could look at relative depths of that and actually recognize abundance. So in this example, on the left, Mark Hannington had done some very elegant work looking at quantitative XRD results from the Skellefteå district in Sweden, and that's a massive sulfide, very old terrain. And he had mapped strong muscovite that basically zoned around the massive sulfides. We were able to go back and look at that same samples when analyzed with a TerraSpec and found that the relationship of the features, the depth of the feature, we were able to use to do exactly the same thing in a much shorter period of time than the quantitative XRD. So again, mapping out where those zones of interest were around the massive sulfides. And critically, through that period, we were looking at illite and muscovite compositions. And that's one of the big stories in spectroscopy. So Scott and Yang had published this very nice paper showing us the compositional changes. This feature here at 2200, you'll have heard about, I'm sure, many times. That is where that trough changes position based on the composition of the mica. Now, it's a little more complicated than that, but that's the fundamentals, and that's what we've worked with for years. We've also been able to look at that feature and get a rough idea of crystallinity, and that's another really useful thing. So we're doing much more than just saying, yes, there's illite, or yes, there's muscovite. We're actually looking at fairly detailed changes in the chemistry. The middle, where the arrow is, shows the illite, and you'll notice that it's a markedly different pattern from the micas, and that's because there's water in illite. And that's a very important difference to see, and it also does affect where the other big feature is at 2200. So that's what we were doing. But what is the current state? What are people doing? What's the industry doing that I view as sort of best practices in, and we'll give you a couple of quick case studies here to show you what some examples. So Dave Cook this morning showed a very beautiful example from Bado Hijau of the porphyry system there and introduced the tectonic setting for me of the Eastern Arc. So Onto deposit, which is the more recent Vale discovery at the far eastern end of that trend that Dave showed this morning. This deposit was essentially a blind discovery. Under this, see on the right, the green capping andesite, so no alteration in that. But under that was a series of porphyries and a sedimentary package on the right and the diatreme, and you can see all these fingers of porphyries coming up, and the outline there of the dashed area is the 0.3% copper shell. So in exploring this, they're essentially in an active geothermal zone. I mean, activity, 100,000 years old is still pretty recent. And they used the TerraSpec to analyze samples on every drill hole, every half meter to meter. So they had detailed mineralogy down every single drill hole. They were able to map the transitions from the upper levels there, where there's actually some kaolinites and lower temperature minerals, down into the lithocap, into the alunite, dicite zone, down into the porphyroid, and further depth into tourmaline and zunite and topaz. And they were able to use this extensively in defining their resource. So that was all done with TerraSpec and also using the Osiris mineral identification. So this is the actual alteration map that they were able to create. And you can see here the very blanket lithocap. And there's a little zone that pokes up in the middle there of quartz porphyroid alunite alteration, but generally a fairly blanketed zone. But they were able to, they knew when they were drilling, as they were drilling, how close they probably were to the mineralized zone and where they were in the system. So here's another example. This is the Kışladağ gold porphyry system in Turkey, in the shown there. And it's been in operation for many years. They had a lot of difficulty in sorting out overprinting alteration assemblages. So very nice alteration, but because of the overprinting, difficult to assign which block to which, particularly in geometallurgy, to which block. So this is the alteration on the left. They had a very strong potassic alteration assemblage. Within that potassic alteration, the active, spectrally active minerals were the biotite, and the amphibole, chlorite, and smectite. They also had a tourmaline white mica assemblage, and in that, there's also quartz and albite, so we can analyze the tourmaline and the white mica. And then lastly, an argillic assemblage with kaolinite, montmorillonite in it. So their original, this was work done by Eldorado Gold, who owns this deposit, and Tim Baker and Sean McKinley at Eldorado Gold wrote a paper that's in economic geology about this work. So this was the original deposit modeling. They very large block kind of assemblages, trying to split up the advanced argillic, the white mica, and not really very helpful. So they were trying to get a better grip on the details of this deposit. So they had a lot of historical spectral work. They also had good references. They knew their mineralogy. They'd done petrography as well, so they knew what they were looking at. And they took that 85,000 spectra and ran it again through the Osiris Mineral ID program. But what they were able to do is take the data showing which mineral, they took cutoffs of the most spectrally active mineral, and they were able to create these zones based on that, which, as you can see, is way more detailed and helpful in terms of mining the deposit than their original modeling. So again, tens of thousands of analyses. So now here's the lesson part. We have to do any of this work, acquire high quality data. And unless all of us know exactly what the data is and how it's acquired, we're going to end up with very poor results. We're going to decide that this tool doesn't work. So we're going to just go through a few slides here to give you that brief lesson on what it is you should be doing, not doing, and what you might want to think about. So this is the electromagnetic spectrum. This is what it's all based on, right? So you have the waveform at the top. In the middle line is the wavelength in microns. So the one right in the middle there, to 1 micron, 1,000 nanometers, that kind of puts you right into the infrared. And then we have the energy that's generated, whether it's electronic, molecular, translational. This, where the box is pretty much where we do a lot of our geological analyses, mineralogical analyses, right? So we use X-ray. We use X-ray diffraction. It gives us crystal lattice structures and tells us structures of minerals. We use the infrared, where from the UV to the visible into the infrared, to actually look at molecular vibrations. So the spectroscopy is actually telling us about molecular bonds, not directly the minerals. And that's really important to know. So we're looking at positions of and presence of aluminum hydroxyl or iron hydroxide, so, or iron oxide in the near infrared. So this is what you're actually measuring, which is hugely valuable. But as I said again, important to understand. So you can have a mineral mixture, and you could have a contribution of aluminum hydroxyl from 2 or 3 different minerals. This is what happens in the analysis. The light shines onto the surface, and then gets reflected to a detector. But because of the molecules are vibrating at these wavelengths, they're absorbing energy. And that energy means you get a trough. So when we see these dips over there on the right in the spectrum, that's where the energy's been absorbed. So how do we figure out what we're looking at? McLean Trott, who's probably in the audience somewhere, he should put his hand up, and a whole bunch of, in the back, a whole bunch of co-authors fairly recently put out a really nice little article in the Applied Geochemist newsletter, Explore, and it goes through a lot of the things, the do's and don'ts of spectroscopy in taking analyses. It also talks about using the Spectral Geologist, which I'll show you, which is a software. And it's a really useful, up-to-date reference for you on actually doing this kind of work. So in his article, he has this nice examples. We tend to show individual spectra like stacked on top of each other. So these are just giving you a relative idea of what on the top is muscovite, in the middle is alunite, and the bottom is chlorite. And again, you can see they have these different troughs. So one of the key things to understand is that we can measure the depth of the trough. We can also measure the width of it. And that comes from this thing we call the hull. And the hull is like a thread draped over the top of the spectrum. And some people correct the hull, and so they pull it straight. When you pull it straight, you actually lose some of the character of the minerals, and you change the wavelength positions. So when you're looking at data, you need to make sure you know how that data was processed. Was it hull corrected or not? Are you comparing apples and oranges or not? So that is key, but really helpful. So when we start measuring depths, or we start looking at wavelength positions, when you get data back from Osiris or whatever, they'll possibly call them scalars or features. This is where the real richness of the information is in this information, not just the mineral identification. So a whole range of minerals that we can identify. I'm sure you've seen these, and the most common field spectrometers give us now the visible through to the shortwave infrared, which is basically 400 to 2,500 nanometers. And there's a whole lot of hydrated minerals and sulfates and carbonates and ammonia that you can see in those wavelengths. These are all the spectrometers. So PIMA up on the top right no longer is available. There's this Ocean Insight instrument, but it's not really set up for geology. And the Agilent down here on the left actually does long wave, not short wave, but that's quite interesting. So if you take those out, this is pretty much what's available. The ASD Halo, unfortunately, has had a supply chain problem recently, so it's not very available. Nice little instrument. So pretty much we're left with these providers that are all ruggedized and intended for use in exploration. You need to ask questions when you're deciding which spectrometer to use. They have different resolution. They have different ways of calibrating. Some have internal reflectance calibrations, some don't. And you need to be aware of those differences. If you're analyzing, this is just briefly, I'll take a picture, I won't go through them all. These are the do's and don'ts. It's pretty straightforward. It's got to be clean, it's got to be dry, it's got to be systematic. You should always run a standard, you should always run Mylar. Every instrument, even when we're talking about drill core scanners, will be different. It might be 1 or 2 nanometers different. When you look at kaolinite, it might be a little bit different from the next instrument. So if you're looking at data sets that combine data from different instruments, you need to have calibrated so that you can actually make a correction for that. If it's wet, if it's sulfides, if it's a pulp, these will not give you good results. Everybody should be making a project reference set. Everybody should have that for every job you work on. You should have some backup petrography or XRD or whatever it is, so you really have characterized your rocks, and you can take your spectroscopy data and take it back to the rocks and calibrate. Validate, calibrate, and the geologist has got that role. It's a very big role. A reminder again that when we're looking at the data, so you get back an analysis that says, oh, this mica and alunite or whatever is in there, you're only seeing what is spectrally active, particularly when we're looking at the shortwave wavelength. You're only seeing what gives a response. So if there's quartz in there or feldspar in there, that is not part of the analysis. So we're not looking at quantitative whole rock mineralogy. So when we do the analysis, there's, as I said before, there's a couple of major ways people do it. In the Spectral Geologist, which McLean Trott's article talks about, you can actually look at individual references. You can do a lot of work yourself if you learn how to use the software appropriately. It will also give you mineral identifications. They, calibrate, get your references, double check, because nothing is 100% correct any of the time. But in this case, it's giving you downhole a set of minerals that's shown by the colored bars on the top, and then another example of plotting the 2200 wavelength, and that's going downhole, and you can see in this particular example, the mica is changing from a 2192, a very low value, up to 2218. So you can see that they're seeing a difference in their mica compositions down the hole. This is the kind of data you can get back from Osiris, which is now runs through Imdex, owns it, and they have also recently released a update to it, so the results, at least from what I read online, are coming back within minutes. It used to be 3 or 4 days. It would upload to the cloud when you put your data in, and then you'd get the results back. Now you're getting them back in virtually real time. So that's a huge advance. It will also give you all the white mica positions. You can play with depths of scalars. You can look at mineralogy. There's a richness of data that you can explore. So that's the portable field spectrometers, and for me, that's the starting place. There's a lot of value in what you can do with them, which is flexible and can be taken from project to project. But what about all the core scanners? What about all the other stuff? So for current work, Richard Guagan at Freiburg is doing some interesting things, and it's published, so you can start to read about the technique of drill core scanning from at least their perspective and see how some of these techniques actually work, and I encourage you to do that. And I encourage you, when you're thinking about drill core scanning, to be asking technical questions about how the technique is working, what the resolutions are, and a whole slew of other questions which are really, really vital. So these are a lot of the options out there for scanners right now. There's TerraCore, CoreScan. CoreScan also now is EpiRock. It also has the high logger in its setup. TerraCore does shortwave, longwave, and the geologger. Then there's also our XRF scanners. And then to the right, there's a couple of providers that are trying to combine everything. Both Geotech and Geologic AI are trying to throw more XRF and spectral stuff together. And then lastly, there's actually some new things happening that maybe into our future we'll be doing more regularly in terms of LIBS analysis of core. So we have this kind of, desire to have more data. So if we do the long wave and the short wave together, then, okay, we're getting more mineralogy, which we'll talk about here, and that works pretty well. If you throw the XRF on as well, then you have a whole question of how much data do you have versus the speed that you're actually able to analyze it. So adding the XRF currently really slows down the amount of data you can acquire on a daily basis. And you can ask the question, can we not get enough out of the spectral data, proxies, other ways of looking at it, to not need to add the XRF onto the same scanner? This is an example of the CoreScan data, so I'm sure you've all seen these, and they have a booth here. These beautiful images of core. So on the left is the photograph, and then on the right are mineral maps. And each little pixel represents a spectrum. So in this case, they've assigned actinolite to that pixel, and that's essentially how that analysis, mineral analysis, is done. So again, when you're talking to people about that data, you need to know what their resolution is on the wavelengths, and you need to know how fast, what speed, because when you change speed, you also change, the results in terms of how accurate it is. But here, we really want to talk about the full spectrum. So we're also getting into the realm of being able to do long wave. So most of you know the short wave and what we've talked about. In the long wave, we can add feldspars, we can add garnet, barite, apatite. The carbonates show up really well for carbonate compositions. And so here is an image from TerraCore that shows their photograph, then the SWIR results in the middle and the long wave on the right. So we're getting pretty close to 100% of the mineralogy. So an example from them, they've been working on a project out in Nevada in the Carlin-type deposits, and you may know Carlin, fine-grained, really difficult rocks to work in, very hard to see the alteration. So here's an example from some of their work. The top bar is what they got from the short wave, which was pretty much very little. But in the long wave, they can start to pick up very distinct patterns that show the carbonate, show decalcification zones, show silicification zones. And they were able to use that, as you can see in this slide, to do a whole new interpretation of mineralizing structures, to identify more favorable horizons. They're working in an area which had been explored by several other companies. There was lots of drill holes, and I guess it's kind of like what Dave described this morning of, last effort. What else can we do? Well, we can do the long wave, and in actual fact, in this case, it really has helped them out to identify a whole new area within their project. This is supported by work done by Rocky Barker and co, published in Economic Geology as well, where they scanned the image in each of these pairs. The one on the left is a micro XRF, so very detailed chemistry on the rock, and on the right is a long wave image. And they were actually able to correlate these two such that from the long wave image, they were virtually getting quantitative mineralogy that correlated with their quantitative XRD. So clearly, in the long wave, we can do a lot more, and that's really exciting. The other instruments out there, which is Geologger. Geologger is a super flexible instrument. It's easy to move around the world. It's fast to take the data. What it does is it takes one scan down the core, and that then gets put into a machine learning data algorithm, which effectively assigns lithotypes to the rock. So you don't get mineralogy. It's using the shortwave wavelength, but you don't get mineralogy. However, it works really well. And we can still go back and decide which each of those types are. We can do our calibrations and we can figure out the mineralogy. So it's really worth considering, particularly in project development and again for geometallurgy. It seems to be very effective and also cost-wise very accessible. And then thinking towards the future, innovation, there is a laser-induced breakdown spectroscopy, LIBS, instrument that's being developed out of Montreal, a company called Emission. And they're talking about doing quantitative mineralogy. They're basically taking that 1,000 nanometer laser and rastering the core and analyzing it for all the light elements. They're giving the sulfides, everything, and mapping mineralogy. They talk about it as fast. It's not fast compared to our spectroscopy. They're really, you're going to do a few meters a day. So it's not something for us yet, but it's really exciting. So that's what industry is doing. They're working with the best industry groups, are working with lots of reference samples. They've got good core libraries. They're using thousands of samples. So what are the challenges? How are we going to reflect? Once in a while we need to step back and think, this sounds great, Anne, we're doing this, we can do it all. We've got wavelength positions, we've got mineral ID. So here's an example of where people are trying to, in the academic world, push forward on what we can get out of the data. And Scott Halley in 2015 had a nice article in SEG Discovery showing wavelength positions in the porphyry system for that 2200 nanometer wavelength for the mica. This is another example which was in a paper about Grasberg, and they're trying to compile a whole bunch of data from a variety of papers to come up with models that actually show wavelength positions and not just alteration minerals. I really like the idea of this. I think there's a lot to get from it, but all that we know right now is that this is wrong, or it's not right, because we're compiling data. We know that it hasn't been cross-calibrated. We know that they're different instruments. They've been taken in different places, in different ways. We don't know the exact wavelengths. And so we have to be really careful about making assumptions that these fairly small differences in wavelength are actually real. The other caution comes from the white micas, and some of this work was done by Jonathan Cloutier. I think he was at CODES when he was doing the work, along with Steve Piercy in Memorial. And what we can see here, which is really important, is that the wavelength position of the white mica changes based on whether you're getting into an illite or whether you're a really crystalline mica. So if you start comparing compositions of illites and micas, you're not looking at the same thing. And the shift, the red line on the bottom right is the key one to look at. The red line is a mica that has cations that are close to 1. It adds up. There's no deficiencies in the structure. It's almost a pure mica without any degradation. As it goes to illite, and as the Chermak substitution happens, which means that iron and magnesium and silica are all substituting for aluminum, so you're not just having a strict cation substitution, that slope changes, which means the wavelength position of the 2200 feature changes. So if you're really trying to do composition of muscovites, muscite to phengite, you really need to have a very clean, nice mica to do it well. And we need more work to really figure this out and to know exactly what we're looking at. And this is part of what Scott Halley is trying to do. When Dave talked this morning about taking mineral compositions and getting them to whole rock, we need much finer, better constrained data that comes from research that shows us exactly what the wavelengths are for the particular mica we're analyzing. And one of the issues is often the spectrometers have a centimeter field of view. Then you're trying to compare it to microprobe data, but you might be in a mixture of minerals. So it's really difficult work, and it's going to take some really good scientists to continue to push that boundary. Alunite is also another question. It also talks about the composition changes in alunite. Well, alunite is very susceptible to whatever the host rock was. So from sodium to potassium compositions change based on host rock. It also changes based on environment of formation. And we know that there's lots of micron scale banding in magmatic hydrothermal alunite. It goes from sodium to potassium in micron scale. And so when we're getting an analysis, we're probably getting an average. What's controlling that? Kinetics, temperature, all the other things still really needs to be thought about. So when it comes to research and academia, we need really to push forward on developing this really robust understanding of the mineral spectral characteristics in relation to the mineral systems. And we need much more industry collaboration with researchers to get the researchers large data sets. The stuff that many industry people are working with is way more than most researchers. And you see so many papers published with, oh, I did 100, here's the SWIR data, 100 samples. We know alteration. Alteration varies from spot to spot. If you're trying to compile a large data set, you need a lot of data to make it statistically relevant. You can't just look at 100 samples and do an alteration map. So we also need to develop continue to develop our techniques, our tools, which is happening mostly through industry, but can be enhanced by what academia has to offer. So this will make us better at understanding our ore bodies and fluid rock processes through both space and time. So the conclusion here for me is that success, yes, the tools, and we have to embrace the tools, but the success of those tools is going to really depend on critical thinking, collaboration, innovation, knowledge sharing, teamwork. None of us can do this by ourselves, and we can really need smart humans involved to make this happen. So I'd like to thank everybody who's ever worked in spectroscopy. It's great, and let's push forward. Thank you.